It's a strange thought, isn't it? We spend our lives governed by simple, intuitive rules. Heavy things fall, dense objects sink. But every so often, human ingenuity creates something that seems to shatter those rules, forcing us to look again at the world and the fundamental forces that shape it. Consider two such marvels, born from the crucible of the early 20th century, each a titan in its own domain. One, a master of the sea. The other, a conqueror of the sky. 100,000 tons of steel, bristling with guns, doesn't sink. This colossal floating fortress, a city of armor plate and intricate machinery, should, by all accounts, plunge straight to the ocean floor. Its very existence feels like a direct challenge to gravity. Yet it sails on, carving through the waves with an unstoppable momentum, a testament to naval engineering that harnessed the very water it sailed upon. And a bag of gas, longer than a city block, doesn't just fall out of the sky. This immense, yet seemingly fragile structure of fabric and lightweight metal, filled with millions of cubic feet of a volatile lifting gas, appears to hang in the air by magic. It's a delicate giant, a cloud given form and purpose, seemingly at the mercy of the slightest breeze. These machines, the battleship and the airship, seem to defy common sense. They represent the pinnacle of opposing philosophies, one achieving dominance through immense weight and density, the other through engineered weightlessness. To the casual observer, they are paradoxes made real, floating and flying in defiance of the natural order. But they don't. They obey it perfectly. Their secret lies not in defying physics, but in exploiting it with breathtaking elegance and precision. They are masterclasses in applied physics, in bending fundamental forces to human will. The battleship floats because its carefully shaped hull displaces a volume of water weighing more than the ship itself. The airship rises for the exact same reason, using a lighter-than-air gas to displace the heavier surrounding atmosphere. Both are triumphs of Archimedes' principle, applied on a staggering scale. And for a brief, intense period in history, they were the ultimate symbols of national power, one ruling the waves, the other aspiring to rule the air. They were the embodiment of technological ambition and military might, promising security and projecting strength across the globe. This is the story of these two giants, the steel Leviathan and the silver Zeppelin, and the shared physical laws that made them possible. Have you ever stood at a port and marveled at a colossal container ship, a floating city of steel weighing hundreds of thousands of tons, and asked yourself a seemingly simple question: how does that float? It appears to defy logic, a massive metal object resting calmly on the water's surface. To unravel this everyday miracle, we need to look beyond the sheer size and delve into the fundamental principles of physics that govern our world. So, let's start with that most basic question. How does a ship float? The answer lies in an epic, yet perfectly balanced, struggle. It all comes down to a battle between two fundamental and opposing forces: gravity and buoyancy. These two forces are in a constant tug of war, and the outcome determines whether an object sinks or floats. First, there's the relentless downward pull of gravity. This is the force that attracts every single particle of the ship, every steel plate, every container, every piece of equipment, towards the center of the Earth. The sum of all this weight acts through a single point known as the ship's center of gravity. Unchecked, gravity would pull the entire vessel straight to the seabed, but it isn't unchecked. Countering this downward pull is the upward force of buoyancy. This isn't a single force, but the result of water pressure. The deeper you go, the greater the pressure. This means the pressure on the bottom of the ship's hull is significantly greater than the pressure on the parts just below the surface. The net effect of all this pressure is a single, powerful upward thrust. Buoyancy pushes it up. So, what determines the strength of this buoyant force? The key is a concept called displacement. Imagine placing a ship into a full bathtub. Water would spill over the sides. When a ship sits in the water, it pushes aside, or displaces, a volume of water exactly equal to the volume of the part of the hull that's submerged. The ocean is simply a much, much larger bathtub. Nature abhors a vacuum, and water is no different. It constantly tries to reclaim the space that the ship's hull has taken. The water, trying to fill that space back in, pushes back with an upward force from every direction on the submerged hull. This crucial insight was famously discovered over 2,000 years ago by the Greek mathematician Archimedes. This is Archimedes' principle. His principle states that the upward buoyant force exerted on a body immersed in a fluid is equal to the weight of the fluid that the body displaces. It's not the volume of displaced water that matters, but its weight. And since salt water is denser than fresh water, it provides a slightly stronger buoyant force for the same volume displaced. This brings us to the moment of truth. The ship will sink into the water, displacing more and more of it, until the weight of that displaced water exactly equals the total weight of the ship. So, if the ship weighs less than the maximum weight of the water it pushes aside, it floats. This is why the concept of density is more important than weight. A ship floats, not because it's light, it clearly isn't, but because its density is less than the water it sits in. It's not about being light, it's about being less dense than the water. To understand this, consider the material itself. Steel is about 8 times denser than water. If you take a solid steel bar, its density is far greater than water's, so it displaces a weight of water far less than its own weight. As a result, a solid steel bar sinks. But what if we change its shape? If you take that same amount of steel and fashion it into a boat or a ship, you are creating a structure that is mostly a pocket of air. You spread the weight over a volume so large that the combined density of the steel and the vast amount of air inside the hull is far less than the density of water. The ship as a whole system becomes less dense than the fluid it's in. The ship finds its equilibrium, its waterline, at the precise point where these two colossal forces, the downward pull of its own weight and the upward push from the weight of the displaced water, achieve a perfect balance. It is in this state of neutral buoyancy, a quiet truce in the war between gravity and the water, that a mountain of steel is able to conquer the sea. Now, take this principle of buoyancy and scale it up with the full force of industrial might. The 19th century wasn't just an age of invention, it was an age of production on a scale never before witnessed. Foundries glowed day and night, turning raw ore into rivers of molten iron. Forges echoed with the rhythmic clang of steam hammers, shaping metal with titanic force. This newfound capacity to manufacture vast quantities of iron and steel didn't just build railways and bridges. It was about to fundamentally reshape the very concept of power on the high seas. For centuries, the formula for naval dominance was clear. Warships were majestic, towering structures of wood, propelled by the wind and armed with rows of cannons. From the Spanish Armada to Nelson's fleet at Trafalgar, the wooden walls of a nation's navy were the ultimate expression of its global reach and military strength. They were complex, beautiful, and the product of generations of shipbuilding knowledge. But their time was coming to an abrupt and violent end. In the mid-19th century, 2 technological revolutions collided with explosive force: the relentless power of steam and the unyielding strength of iron armor. Steam engines, already revolutionizing factories and land transport, promised to free ships from the tyranny of the wind, offering consistent speed and maneuverability in any weather. Simultaneously, the ability to mass-produce thick iron plates offered a defense that traditional cannonballs simply could not penetrate. The first true children of this new era, ironclads like the CSS Virginia and the USS Monitor, were bizarre, almost alien-looking vessels. They were low-slung, smoke-belching fortresses of metal that bore little resemblance to the elegant sailing ships they were built to destroy. When they met in battle, they changed naval warfare overnight. The results were decisive. Wooden ships couldn't hurt them. Cannonballs that would have torn through oak hulls simply bounced off their sloped iron sides, sparking harmlessly. An entire fleet of traditional warships could be rendered obsolete by a single one of these new iron monsters. Every major naval power scrambled to build their own. But this new paradigm came with a fundamental, inescapable problem. Iron is heavy. Incredibly heavy. A square foot of 4-inch thick iron plate weighs over 160 pounds. Now imagine cladding an entire warship, hundreds of feet long, in that material. The sheer mass was staggering. To keep all that weight afloat, the laws of physics demanded a trade-off. The hull had to be bigger, displacing a much larger volume of water to generate the necessary buoyant force. The displacement, the weight of the water a ship pushes aside, had to equal the total weight of the ship itself. This began a naval arms race defined not just by the number of ships, but by a complex engineering challenge that can be visualized as a physics triangle, with three competing virtues at its corners: armor, firepower, and speed. The unforgiving reality was that you could only ever maximize two of these qualities at the expense of the third. The limiting factor was always weight. Want a heavily armored ship with massive guns? It would be slow. Want a fast, heavily armed vessel? Its armor would have to be thin. A fast, well-protected ship. It would have to sacrifice the weight of larger, more powerful cannons. This created a vicious design cycle. More armor added weight, which meant a deeper, wider hull was needed for buoyancy. This larger submerged profile created more hydrodynamic drag, which required a bigger, more powerful engine to maintain speed. But a bigger engine and the coal to fuel it added even more weight, which in turn required an even larger hull. For naval architects, it was a constant, maddening engineering puzzle. Every design was a compromise, a delicate balancing act between these three competing priorities, with the fate of nations hanging on their calculations.